Okay, I started the recording now, so we will have the course online a bit later for those who cannot be here. Okay? Today, the idea is to start a new chapter, but before we do that, I wanted to ask you if you have questions regarding the last exercises we did about energy. Okay, as you remember, I added a few exercises to the course because I felt they were not enough. And last week we did the course offline with the video. Were you able to do the exercise? Did you follow this video?
Yes.
You did?
Yes.
Yeah? Okay. And you got it? You have the correction of the exercises? You understood? Or you have questions about these exercises?
No, it's okay.
It's okay. Good. So in that case, if nobody has a question, we are going to start the new course, okay, which is called Temperature and Heat. And I don't know why there is a 1 here. There should not be a 1. I don't know why that happens. Okay. So what's the plan of the course? We are going to start with some definitions of temperature and heat. And then we will discuss the law which is connecting them. Okay? The first thing I need to do with you is to convince you that temperature and heat are two different things. It's not the same, and it's often confused in standard language. Okay? Especially in French. In English, the vocabulary is a bit different. But in French you have chaleur, which means heat, and then when you say that something is chaud, it's related by the word to heat, but actually it refers to temperature. So in French there is a lot of confusion in the terminology. In English there is a bit less, but still. Okay, I would like us today to think about these two concepts of temperature and heat. Okay, maybe you have some ideas about that. How would you define temperature and heat? Do you have an idea about that? As to
like
how
temperature is the speed at which the molecules they move around.
You read the course in advance, so you know all that.
Yeah, no, I didn't read it, but
Okay.
It's in my brain.
So indeed, temperature is a measure of the local agitation of molecules. Okay? Yeah, you know that when you have matter in some state, let's say you have matter, and these things are atoms inside matter. Let's say it's a solid. Well, all these atoms, they vibrate, which I draw like this.
On a paper right now. We can't see it. Like we just see
Ah, yes, because I forgot to share the screen. I'm very sorry. Sorry. Thank you for telling me. So now I need to go into presentation mode. Sorry. Okay, and so now you should see my paper. Does that work?
Yeah.
Okay,
Yeah.
so here I wrote temperature and heat. I wrote here the definition of temperature, measure of the local agitation of molecules, and heat, we are not there yet. And then here I drew matter with some atoms, okay? Let's say it's a solid, the atoms are in place, but they vibrate, they move very fast around their equilibrium position, they vibrate, and this vibration is related to temperature. Okay, so when you measure temperature, you measure the kinetic energy of the atoms at a given place in the system. Okay, this is why here in the definition of temperature I said measure of the local agitation of molecules. It means if you have a substance, okay, and maybe you heat up this substance with a flame, you will have a certain temperature down here, you will have a different temperature up here, you will have a different temperature here. So you can have a different temperature in the same system, okay, because the local agitation of molecules is different in different parts of the system. Okay. Now, what is heat? Okay, heat is the sum of all agitation energy in the system. So heat depends on the size of the system. If you have a system which is twice bigger, it will contain twice as much heat. Okay, if I have one system at, let's say, 20 degrees, and now I have a bigger system, a system which is double the size, and everything is at 20 degrees, this system will contain twice as much heat than this one, because this system here has more molecules being agitated, and so it contains more agitation energy. Okay, so the heat is not you cannot say here there is a heat of something and here there is a heat of something. It depends on the whole system. Okay, we will see examples. You will understand that better in a moment. Let's take the course and let's see what it says. Okay, the first thing is we are going to analyze some real life cases. Okay, case one, let's read it together. We take a swimmer. The internal temperature of his body is 37 degrees. The swimmer is swimming in the sea, and the sea is at 20 degrees. The water is at 20 degrees. He or she has a sensation of cold. Therefore, he or she loses heat. We will note this heat loss by Q. However, the swimmer temperature remains at 37 degrees. Okay, when you are in water, you are swimming in water. Let's say you are here. Oh God, I have to draw a swimmer. Yeah, don't laugh, and draw a swimmer for me because it's very early. I'm still sleepy. Okay. When you have a swimmer, you have water at 20 degrees, the swimmer is at 37 degrees. Obviously, you know that if you are in water and the water is colder than your body, you will lose heat, and after a while you will feel cold. Okay, so you are losing heat here. Your body is losing heat to the water, but the temperature of your body remains the same. Okay, so this is an indication that heat and temperature are different, because heat, you are losing it. Okay, you are losing heat, but temperature remains constant. Okay, why does temperature remain constant? You have an idea? How come if we are at 37 degrees and we swim in water at 20, how come the temperature of our body remains at 37? Huh? Hello?
Like, maybe the molecules, they still move at the same speed.
Yeah, but why?
It's just that there is less of them, and that
it's just
so
the fact.
is,
It's just the fact that our body produces heat. Okay, our body uses food, the calories which are in food. Calories are a unit of energy. It uses these calories and transforms the sugar into heat, which keeps our body warm. Okay, so there is a source of heat in our body. This heat is lost to the water, but the temperatures, they don't change, because our body has the capacity to manage its own temperature and to keep it constant. Okay, so this is an indication that heat and temperature are not the same thing. Now let's take the second case. Let us walk in the woods while the wolf is not there. The outside temperature is 20. It feels good. Okay, so here we are walking in the woods. This drawing is going to be much easier. We are walking in the woods. The outside temperature is 20 degrees, but we feel fine. How come here we feel fine, and here, where the temperature of the water was 20 degrees, we felt cold? What do you think?
Because we're not en maillot de bain in the forest.
Okay, then suppose you are in maillot de bain, if you want, to make things comparable. What's the difference between being in water at 20 degrees and being in air at 20 degrees? It's a question of energy transmission. The water is a good, transmits energy, heat very easily, while air isolates thermal energy. Okay, so we lose less energy inside air because air is going to take less energy from our body. Okay, air is a thermal insulator, unlike water. Okay, and now if we are in the same forest but suddenly there is a wind blowing, then what is going on? You will feel cold. Why you will feel cold? Because the wind blowing will take more thermal energy from your body. So again, there is a transfer of energy, but the temperature of your body is not changing. Listen, I will not read with you the course in details because this is something you can do privately. I'm just going to talk, and then you are going to read the course by yourselves. Okay, the main thing I want to get to, and this is very, very, very important, is the fact that temperature and heat are different things. Okay, physically they are very different things, and it would be nice not to confuse them. Okay, and as I told you before, temperature is a local measurement of the thermal agitation of molecules, while heat is a form of energy. You remember that from the previous course. Okay, it's a form of energy, and it is given by the sum of all the kinetic energies of the molecules. Basically, that is what I would like you to remember from that. Okay? Now, well, you have the definitions here, so let's read the definitions together. Okay, definition of temperature. The temperature of a material is a measure of the average kinetic energy of the molecules that make up the material. Okay, this is what I told you. The absolute zero is defined as the temperature at which the molecules have zero kinetic energy, which is why it is impossible for anything to be colder. So that's something important. Okay, let's imagine we take a system. Okay, let's imagine, and this system has an initial temperature of 20 degrees, and we cool this system. Okay, we cooling this system. Do you think we can cool it infinitely, or there is some limit? Do you think there is some minimal temperature in the universe, or you can just make something as cold as you want? For instance, minus 2500 degrees Celsius. Is this possible?
No.
No? Why?
Because there's a limit around 273, I think.
Yeah, exactly. So this we cannot have, but there's a limit at minus 273.15 degrees Celsius. Okay, and how do you see this lower limit on temperature? Why can we not go lower than that? Do you have an idea?
I think. Oops. The properties of the matter changes.
Sorry, I didn't understand.
The properties of the matter changes at this point.
The properties of what?
The matter, la matière.
The properties of matter. What do you mean by that? Yeah, lots of things happen at 0 degrees, but it depends on which matter. In terms of temperature, okay? Look, I told you that temperature is a measure of the average kinetic energy of the molecules in a system. So let's take a system at 100 degrees Celsius, at 0 degrees Celsius, at minus 100 degrees Celsius, and at minus 273.15. Okay, and let's imagine this matter is made up of molecules or atoms. I will just draw 6 of them. Okay, at a temperature of 100 degrees, these guys, they are moving around like crazy. Okay, there is a huge agitation. Well, huge, it can be bigger, but it's quite big. There is agitation of the molecules. They all move with respect to each other very fast. They vibrate around a stable position. If we are in a solid state, if we are in a liquid state, it's even more disordered. Now, if you go from 100 degrees to 0 degrees, what you will notice mainly is that these molecules, they move less. Okay, and as you decrease the temperature, since temperature is a measure of local agitation, when you decrease temperature, you decrease this motion of the particles, which I draw like this by little stars, indicating that they move around a stable position. And now if we are at minus 273.15, what happens is that there is no more agitation. Okay, at minus 273.15, the molecules, the atoms, they don't move, they don't vibrate, they are totally still. And cooling them down would mean making them more still. But how can you be more still than not moving? You cannot. Okay. So at some point, when matter is completely at rest, when atoms are completely at rest, you cannot go lower. And this represents a lower limit in the universe. Okay, it's a very wide phenomenon, which is valid everywhere. And this state here at minus 273.15, we call it the absolute zero. Okay, this temperature is the absolute zero. And so physicists had the idea of defining a temperature scale which starts at 0 here, okay, and which then increases like the Celsius scale. So what you have in terms of temperature scale is one scale, which is the scale of Celsius, okay, and this scale starts at minus 273.15. Okay, this is the lower limit. And then you have 0 degrees, you have 100 degrees, and this is defined. How is 0 degrees defined? You know? Yeah, you know. Okay, 0 degrees is defined as the temperature at which water freezes at sea level, and 100 degrees is the boiling temperature of water. Okay, so Celsius had the very good idea to connect his energy scale to physical phenomena which are very relevant to everyday's life. When the water freezes, you know that it's 0 degrees, and when water boils, you know that it's 100 degrees, and water is one of the main elements determining life on Earth. Okay? And the idea was to introduce another scale which starts at 0. This is the Kelvin scale. Kelvin was a British physicist. This is the Kelvin scale. You start at 0 Kelvin, at the absolute 0. So 0 Kelvin is equal to minus 273.15 centigrade. And the scale has the same spacing here between the degrees as the Celsius scale. Okay? So how much would it be here for 0 degrees in Kelvin? What would you say? We shifted everything down. Okay? So between here and here there is 273.15, and so the 0 degrees Celsius will be equal to 273.15 kelvins. Okay? And now how much would be 100 degrees Celsius? Well, you just add
173.
exactly. You just add 100 degrees and you get 373.15. Okay, so you see the Kelvin scale, this is the real physical scale, because it starts at 0 Kelvin at the absolute 0, and then it has the same spacing as the Celsius scale. So the temperature of freezing water is not any round number, it's 273.15. The temperature of boiling water is 273.15, etc. But on this you have a scale which is related to the absolute 0. Okay? And so you have a formula to transform one into the other, which is very simple, but you have to write it in the course because something terrible happened with the PDF. I don't know why there is. You have that too?
Yeah.
You have this thing. Okay, so remove it and replace it by this definition. The temperature in Kelvin is the temperature in Celsius plus 273.15. Okay? This is the relation that should be written here in this space. Let me erase it. Okay? So now if you have, for instance, 273.15 Kelvin and you are wondering how many degrees it is, well, you just replace it here and you have your answer. It gives you 0 Celsius. If you have 293.15 Kelvin, then here the temperature in Celsius is 20. If you have 373.15, the temperature in Celsius is 100. Okay? So the two main temperature scales are Celsius and Kelvin. The Celsius scale is based on water, which is a good idea because, as I said, water is an essential element of life. All living creatures contain a lot of water, so it makes sense. Okay, and then the Kelvin scale is related to molecular agitation. Okay, and this is the real physical scale. And in some cases we will need to use that scale to solve physics problem and not this one if the phenomenon we have is connected to the absolute 0. And then, as you probably know, there is another temperature scale which is the Fahrenheit scale. Okay, so the Fahrenheit scale is something I don't like to teach because I find it extremely stupid, the scale. It is not based on anything which makes sense in real life. Fahrenheit, he took as 0 degrees the coldest stuff he could create in his lab, and the coldest stuff he could create in his lab was cooled salted water, and with that he managed to get to minus 15 degrees Celsius or something like that, and he called that zero. Okay, and then he measured kind of the temperature of living beings, and he decided that this is 100 degrees, and he did a scale which is not linear and which is a mess. And you have an illustration here of these three scales. So you see, if we start with the Kelvin scale at 0 Kelvin, this is equivalent to minus 273.15 Celsius, this we already said, and this is equivalent to minus 459.58 Fahrenheit. Okay, and then here at 0 degrees Celsius you have 32 Fahrenheit, so the 0 Fahrenheit is a bit lower here. It's the temperature of this lowest, the coolest thing he had in his lab, and then the temperature increases, and when you get around 37 degrees you get at approximately 100 degrees Fahrenheit. So as I told you, 100 degrees Fahrenheit represents the temperature of living animals. Okay, mean people say that 100 degrees Fahrenheit corresponds to the anal temperature of a cow, but it's not exactly right, but it's not that wrong either. Okay, and water boils at 212 degrees, so this scale makes just no sense. Okay, and for physical purposes we will never use it because this scale has nothing physical. So you don't need to know that. I will never question you about the Fahrenheit scale. This is not a physical scale. And if you want, you have here the transformations between these different scales. Okay, this is the one I told you before. Temperature in Kelvin is equal to temperature in centigrades plus 273.15, and then here you have the formulas which allow you to transform centigrade into Fahrenheit and inversely Fahrenheit into centigrades. Okay, but this is something you don't need to know that. I will not interrogate you on that. Okay, just know that there are these different temperature scales. Okay, good. Now we are going to do a number of experiments. Okay, I would like to get to a formula which gives me heat. We will call heat Q. Okay, the letter for heat is Q. Okay, and I would like to find an expression where Q is related to temperature. Okay, I would like to know how Q is related to temperature, and to establish this formula I will do experiments. I will do three experiments. Okay, first I will take some quantity of matter and I will heat it up, and then I will take the double quantity of matter and I will heat it up, and I will see how much energy is needed to heat up these 2 kilos instead of 1 kilos. Okay, then I will what was the second experiment? Oh yeah,
so it's 1 and 2 kilos of water
or anything else. It could be iron, it could be what you want. We will get back to that. Okay, first experiment I will warm up 1 kilos and 2 kilos. Second experiment, I will warm up, let's say, from 20 to 40 degrees and from 20 to 60 degrees. Okay, here I have a 20 degrees difference, here I have a 40 degrees difference. What is the energy that I need to give this thing so that we get to the same final temperature? We will take that in details, and then I will take one material and another material, and I will see if it's the same for all materials or if some materials need more heat than others. Okay, so we are going to do all these experiments. We call these thought experiments. We could also heat up stuff in the lab, but this we cannot do that. So we will do thought experiments. Okay? So let's read that. The first experiment I want to do is heating up some amount of matter and the double amount. Okay? So we take, let's draw this. We take 200 grams of water and we heat it up to increase the temperature from 10 to 70 degrees Celsius. Okay? And then we heat up 400 grams. So let me do it a bit bigger. We heat up 400 grams again from 10 to 70 degrees Celsius. Okay? Well, what do you observe when you do that? Let's assume that here I warm this thing with a certain type of flame for a certain time. What would you say we need here? We need to heat up the same. We need to heat up with two flames like that. What would you say? Intuitively, if we heat up the double amount, well,
it should take the double of time.
If we want it to take the same time, then we need to heat it up with two flames. Okay, we need the double of energy to heat up 400 grams from 10 to 70 as to heat up 200 grams from 10 to 70. Okay, so we need the double energy if we double the mass. Okay, this makes sense. And so the first conclusion we draw is that the quantity of energy necessary to heat up something is proportional to the mass. If we heat up twice the mass, we need twice the energy. Okay? Do you agree with that?
Yeah. What does the F mean?
Sorry?
Like in between. There's a sign that's in between Q and M.
The signs means proportional to.
Okay, thank you.
Okay, you can also use a little wave, but it's not an alpha. Okay, it's a sign. It's different from alpha. Okay, so the quantity of energy which we need to give to somebody is proportional to the mass of the body, and the mass is the quantity of matter. It makes sense. Okay, now let's do a second experiment to see how this depends on temperature. Okay, what if we heat up a system by 20 degrees and we heat up the same system by 40 degrees? What is the difference? I'm asking my camera to focus. Thank you. So let's do the second experiment. We take 200 grams of water, for instance, and from 10 to 30, okay, and we heat it up from 10 to 30 degrees, and we observe how much heat is needed. Okay, and then we take the same quantity of water, 200 grams, and we warm it up from 10 to 50 degrees. Okay, so in the first case, the delta T, the difference between the end temperature and the initial temperature, is 20 degrees. In the second case, the delta T is 40 degrees. Now, what do you think intuitively? In order to heat up the same quantity but by the double temperature difference, we will need more energy, less energy, the same energy? What would you say?
I'd say the double, but
yeah, the double, because you need one of these burners to go 20 degrees, and then if you want to go the double, you need two sources of heat. Okay, so what do we learn from that? We learn that the quantity of energy you have to give to a system is proportional to the temperature difference, if you want to heat it up by twice as many degrees, you will need to give it twice the same amount of energy. Okay? All this is valid if you don't go through state changes. Okay? So as long as you are yeah.
I just don't understand something.
Yeah.
So it's about the minus 273.15 degrees. So this means...
Well, no, this is not related to temperature scales. Well, I don't understand your question.
No, it's just, it was just before that, even before. So when we cool it, is it the same thing when we cool it down? So if we want to cool something down faster, we would like to take...
Oh, yes.
We have to take like 2 times...
Oh yes, it's the same. But I'm doing it while warming things up because it's easier to illustrate, okay, with little burners, etc. But of course, these differences, what we say here remains true if the temperature decreases, okay. But here I would say I decrease the temperature by 20 degrees, and here I decrease the temperature by 40 degrees. Well, here maybe you need 1 fridge, and here you need 2 fridges. Okay, but it's more difficult to illustrate. But your point is correct. All this works whether the delta T is positive or negative. Okay, because the equation we are going to derive describes how we transfer energy to a system, but it also describes how we can draw energy from one system. Okay? So for the moment, did I answer your question? Are you happy?
Yeah, I'm happy.
You're happy. Good. Okay. So now let's do a third experiment, and let us heat up different substances. And you will see, if you do the experiment, that heating up different substances takes a very different time and takes very different energy. Not all substances need the same energy to increase by the same amount their temperature. Okay, and here there is a constant which is going to enter our equation, and this constant is going to express how much energy is needed for a specific metal. Okay, and this constant which we are going to introduce is called specific heat. Okay, in French I tell you the word because maybe you will read stuff in French. This is la chaleur massique. Okay, it's called specific heat. So what is the specific heat? For instance, let's take water. Okay, the water has a specific heat. The letter for specific heat is C. So the C of water is 4,180 joules per kilogram per degree. Centigrade or Kelvin, it doesn't change. What does that mean? It means that if you want to heat up 1 kilo of water by 1 degree, you need to give to the system 4,180 joules. Okay? The units indicate what it is. Okay? It's the number of joules, because heat is an energy, the number of joules you need to heat up 1 kilo of water by 1 degree. I can give you another example. The C of lead. You know what lead is? Lead, le plomb. You know, the heavy metal, le plomb. Okay, this is 130 joules per kilo per degree centigrade. So you have values which are very, very different. Lead is one of the lowest ones. Water is one of the highest ones. And you can see here the values, the different values. Okay, you see lead, it's here, 130. Water, where's water? Water is here, 4,180. You should have oil somewhere. No, we don't have oil. Oil is about 2000. Steam is about 2000. Metals are very low, have very low Cs. So this constant, the specific heat, characterizes the material. Okay. So now, what do we conclude from this discussion, which I will let you reread tranquillement? What do we learn? We learn that the quantity of energy that you need to warm up something is proportional to the mass of this something. This was our first experiment. If we take double the mass, we need double the energy. Then we saw that the quantity of energy is proportional to the temperature increase. If we want to heat up by 40 degrees, we will need twice as much energy as if we heat up by 20 degrees. Okay? And the last thing we saw is that Q has to depend on some parameter which is specific about the material, because not all materials react the same way. Okay? And so now we are going to put all this together. If Q is proportional to the mass, if Q is proportional to the temperature difference, and if Q is proportional to some constant C, now we can write a formula which is this. Okay? So this is a formula that we have constructed based on experiment. Okay? The quantity of energy which you need to heat up some mass m by some temperature difference delta T of some material described by the C gives you Q. This is a very important equation that we will use in the rest of the chapter, and I wanted to get to that this morning so we can start doing some little calculations. Okay? So m is the mass. What is the unit of the mass?
Kilograms.
It's kilograms. Delta T is the temperature difference. Temperature difference. Difference between what and what? Well, it's difference between the final temperature and the initial temperature. Be very careful, it has to be in this order. It's the final temperature minus the initial temperature. So if you heat up something, the delta T is positive. If you cool down something, the delta T will be negative. Okay? And this quantity here is in degrees Celsius or in kelvins. Usually we can use degrees Celsius. It's similar because we are counting a difference. Okay? And a difference it's the same whether you use the Celsius scale or the Kelvin scale, because the differences are preserved. And the C, it's in which units? It's in joules per kilogram per degrees. So you see that if you take all these units together, the kilograms, the joules per kilograms per centigrades, and the centigrades, all these, the kilograms, they disappear because you have kilograms over kilograms. The degrees, they disappear because you have degrees over degrees, and you are left with joules, which is the right unit for energy. Okay? Maybe you are a bit confused. So let me give you one practical example. What energy does, oh God, I'm inventing an exercise. What energy does it take to warm up a piece of iron, a piece of 10 kilos of iron from 10 degrees Celsius to 150 degrees Celsius? Okay? How could you compute that? Well, it's very simple. The energy which you need is given by the mass times the C times delta T, and C is the C of iron. Okay? You have to know which material you are dealing with. Now the C of iron, I hope we have it in this table. Yes, we have it. On the second line, iron is 450. Okay, the value of this is 450 joules per degrees per kilogram. Okay, then our delta T is going to be the final temperature, 150, minus the initial temperature, 10, and the mass is 10 kilos. Okay, so we can compute that. We have 10 kilos times 450 times 140, and that gives us how much? That gives
630,000.
how much?
630,000.
630,000 joules. Okay, so you need 630,000 joules to heat up 10 kilos of iron from 10 to 70 degrees. Okay, this was one first example.
From 10 to 150 degrees.
Yeah, 10 to 150. Okay,
Yeah.
second example. What energy does it take? I will put the does it take in little entre guillemets because you will see why. To cool down 125 kilos of marble from 30 degrees to 5 degrees. Okay, well, how you do that? It's the same formula. Q is equal to mc, and now it's the C of the marble. Okay, so the mass is 125. The C of the marble, you can find it in the table on the previous page. It's 880. And then the delta T is what? And here you need to be very careful. Okay, the delta T is the final temperature minus the initial temperature, always. This is how the delta T is defined. What is the final temperature here?
5.
5. What is the initial temperature?
30.
30. So you see that here, this guy gives you minus 25. Okay? And so the quantity of energy, if you cool down something, is going to be negative. This means the system is giving you back the energy. When you cool it down, you actually take energy from a system. Okay, this is what a fridge does. A fridge takes the heat inside the fridge, removes it, and puts it outside. That's why it's warm behind a fridge, because the temperature is, the heat is evacuated. So now if I do this calculation, did you do it, Aniela? Or not yet?
Yeah. Minus.
No, sorry, who is the voice who is always talking and doing the calculations? It's not Aniela.
It's Nicolas.
Ah, it's Nicolas. Okay. So you did you compute it?
Yeah, it's minus 2,750,000 joules.
Okay. You see, if I take 125 kilos of marble and I cool it down from 30 to 5 degrees, it will give me back this thermal energy which was initially contained in the marble. Okay? Okay. I would like to stop theory, but I had to do a bit of theory before we can do exercises. The exercises are not difficult. Okay? So here we have this famous law. Okay? Q is equal to mc delta T. And now we have some problems here that we can do. Okay? The first problem is easy. Write down the MKSA units for heat, temperature, and specific heat. Then check that equation Q equals MC delta T is dimensionally consistent. We did it before, but I want to do it formally here. Okay? The unit of Q is what? You remember? Joules. Okay, it's an energy. Yeah. The unit of temperature is, let's say, degrees Celsius or Kelvin. Just one little comment, you don't say degrees Kelvin. If you say degrees Kelvin, you don't sound like a physicist, okay? You say kelvins, not degrees, where you say degrees Celsius. Okay, now what's the unit of the specific heat? We said it before, it's joules per kilo per centigrade or joules per kilo per Kelvin. It's the same. Okay, and so now the equation Q is equal to MC delta T. If you look at the units, the mass is kilograms, the C is joules per kilograms per centigrade, and the delta T is centigrades. And so the kilograms, they disappear, the C's, they disappear, and you are left with joules for Q, which is correct. Okay? And now we have some very simple exercises which I'm going to ask you to do, and then we will correct. How much heat is needed to warm up 500 grams of water from 20 to 80 degrees? So you can use the values on the table on page 7 for the specific heats, and you can compute that. So here you are going to have different specific heats, and you will have different results for the different materials. Okay, you want to try to do that?
Yep.
Okay. Lots of people have arrived. You're almost all here. You're a very nice class. I have some classes which are demotivating, but you are not. And I'm writing down who is online, not because I want to check you, but because when we will have class councils, if one of you is in a difficult situation after the first semester, and we discuss promotion, I can say, listen, this guy has been online all the time, I have checked, etc., so he has done work. I can say positive things. Whereas if I don't have any info, I cannot say anything. That's why I'm writing down who is here, who is not here. Alexandre is here. Alia, where is my beloved Alia? She's here. Dana is now here. Emma. Yes. Danielle. Yes. Love, my love. Hello was not here in the beginning. Maria, Naima. Maria. Are you calling me?
Yeah.
Yeah.
Yeah, for the exercise 2, the question B, we can't go for ice from 20 degrees to 80 degrees, so we must start at 0.
Where?
For the question B.
Yeah.
Because ice can't be at 20 degrees.
Yeah, you're right. Oh God. So take something else. Take what can we take in this table? Oh God, where's the table now? I lost the table. Whatever. Take rubber.
Okay, thank you.
Okay. Where was I? Nicolas. It's here. Olga. I'm a bit worried about Santiago, but I'm sure if he doesn't do anything, his father will scream. Because I've seen his father at the parents' evening, and he's not joking, this guy. He's very worried about his son not studying, etc. Okay, are you done? Can we do it together? Can I correct?
No.
No. Okay.
Like I still have the point 3 and 4 to do.
3 and 4.
No, actually no.
No, do just
no,
2.
I don't have to do it actually.
Do just 2. You have D and E to do. But it's always the same thing. Okay.
Yeah, that's
How
it.
much heat is needed to warm up 500 grams of water? You just have to be careful about units, okay? So the energy here is mc delta T. The mass is 500 grams. So be very careful to put the mass in kilograms, of course, as usual. Then the C for water is 4180. I'm used to this value. In the table they give 86, whatever. I mean, this is acceptable. And then delta T is the final temperature, so 80 minus the initial temperature, 20. Okay? How much is that? Did you compute it?
It's 125,400.
120 times 25,400 joules. I'm trusting you. Sounds okay. Okay. Now, same question for 500 grams of ice. This is very stupid as a mistake. I'm very sorry about that. So again, it's mc delta T. It's 0.5. Now the C of the rubber, you have it in the table. It's 1,700. Okay, and the delta T is the same, 80 minus 20. So this gives you how much?
51,000.
How much? Sorry?
51,000
51,000.
joules.
000 joules. Okay, you see, you have for rubber a specific heat which is about half of that of the water. It is less than half, and so the resulting energy to go from the same initial temperature to the same final temperature is about twice as big. I mean, more than oh God, it's about half, not twice as big. It's about half. Okay, so this coefficient here is very important. It determines how the different substances are absorbing and giving up heat. Okay, and now if I do it with lead, I will find a ridiculous result because lead has a ridiculous specific heat. So it's going to be 0.5 times 130 times 80 minus 20, and this gives you how much?
We have 3,900.
3,900 joules. Okay, you see, lead is much easier to warm up than water, and this is something we don't really have a physical intuition about that, because when you look at lead, you think, oh, it's very heavy, it must take a lot of energy to heat that up, and no, it doesn't. Okay, whereas you look at water, it takes a lot of energy to warm up water. Okay, why? Well, it's just like that. The advantage with water is that if it takes a lot of energy to warm it up, it also means that when water is cooling down, it can give you back more energy. Okay, so the capacity of water to transport heat is very big. If you heat water in one place and you move this water with a tube to another place, it's a very efficient way to transport thermal energy, and this is how central heating is done. Okay, central heating, it's a circuit of water that gets heated up at some place, and then this water is distributed in the whole building, and in the radiators it gives back its thermal energy that it's carrying with it. Okay, now 500 grams of air. Haha, do we have the value here for the air in that table? Yes, we have the value 718. Okay, so let's compute mc delta T. So the mass is 0.5. The C of air is 718, and the delta T, it's again 80 minus 20. How much is that giving you? You can
21,540.
Okay. The result is not so surprising with respect to the other results. Okay. Now, what is more interesting is this. Okay. How much is 1 kilo of air? Half a kilo of air. It's how many cubic meters of air? You know that? You know the specific
Maybe
mass of air? You know it? You know the specific mass of water, okay? It's 1,000 kilo per cubic meter. For air, it's 1.3 kilograms per cubic meters, okay? If you take 1 cubic meter of air and you are a bit smart to be able to measure it, which means you take a container, you pull a vacuum inside the container, you weight the container, and then you put air into that container and you weight it again, you will see a difference, and the difference will be 1.3 kilograms per cubic meter of content. So 0.5 kilos of air is about half a cubic meter, something like that. Okay, so if you want to know how much your heating needs to produce in order to cool, in order to warm up your house, you can compute the volume of air and then the energy which is needed to heat up this volume of air. Okay, last one, for cooling down 500 grams of water. This is more interesting. It's mc delta T, but the delta T is the final temperature minus the initial temperature, so it's 0.5 times the C of water, which is 4,180, times the final temperature, which is what now?
That's 30.
30, okay, minus the initial temperature 90, and so this gives you minus 60, and how much is the result?
it's the same as the first one we did, but with the minus in front.
Because the first
So,
one, wait, the first one, it was 120, so it was 20 to 80 degrees, so 60 degrees difference. And here we also have 60 degrees difference, correct? So this is minus 125,400 joules, okay? So the convention that is that if Q is positive, it means that you are giving this energy to the system, and if Q is negative, it means you are taking this energy from the system. Okay, you want to try to do number 3? It's not difficult. Okay, it's about power and what we did before. Okay, you need to compute the energy that it takes to warm up these 500 grams of water. We already know the result. And assuming that the power of the heating device is 800 watts, how much time should it work? So this you should be able to do. You don't need to recalculate the Q. Okay, the Q is the one we calculated before. It's 125,400 joules. Or maybe I could let you do this exercise for the next course and stop here. Because if I continue now, we will have again a chapter of theory to do, and I don't want to rush it. We have time. Okay? But what I would like you to do is to take some time to read the course that we went through fast this morning. Okay? So maybe if you agree, we could stop here, because I don't want to overload you. I've already given lots of theory today. I would like you to reread the course, the pages we did until now, and to take a quiet look at that. And then maybe you can finish this exercise and we take it from here next time, because next time we will consider what happens when we mix different substances at different temperatures. I don't want to start this now. I mean, it's a bit of a rush. Okay? Can we do like that?
Yes.
Hmm?
Of course.
Yeah, it sounds good. Yeah.
Okay. So I will, now I have changed my approach with Classroom. I will put the homework on Classroom. So you know what you have to do, but basically I would like you to reread the first 9 pages, try to understand them tranquillement, and then do these exercises 3 and 4, and that's it. And so next time we can start the new theory chapter. Okay?
Okay.
Good.
Alright.
Okay, so I will now put the video online for those who want to see it again. And I see you next Tuesday, and we will correct this exercise and continue. Okay?
Okay. Bye.
Have a good day. Bye bye. Bye bye.
Goodbye.